Progress is impossible without change, and those who cannot change their minds cannot change anything. Hi all, Dr. Clark here again. And for this lecture, we're going to talk about the geosphere. We left off talking about the atmosphere and the different layers of the atmosphere, the different roles that each layer has in the atmosphere, and kind of the history of the atmosphere. How did the atmosphere form? This lecture, we're going to talk about the geosphere, which, like I said before, all of the spheres interact with each other. The geosphere is the sphere that basically, when you say that is the ground, or that is rocks, or that is soil, or that is sediment, or that is something along those lines, you're talking about the geosphere. You're talking about the abiotic, non-living material that makes up our planet. Okay? It's made of, the geosphere itself is made out of the crust, the mantle, the outer core, and the inner core. And we'll come back and we'll dive into this a lot deeper to figure out what each one of these are comprised of and the role it plays on the planet. Okay, so what is the geosphere? Solid earth. Okay, so that's rocks, beaches. Again, like I said, abiotic material. In science, when you see a in front of a word, it means non. Okay, it means non. So abiotic means non-biotic. Biotic means living. So this means non-living material. So rocks, pebbles, sediment, things that you would put together from molecules that are on the periodic table, elements that are on the periodic table that can, make solid forms of material, non-living material. Geo means earth in Greek, and so that's where that geo is coming from. Geosphere is the earth sphere. What is not included in the geosphere, but you might say is not alive? Well, water. Okay? So water is not a living material and would, under many circumstances, be lumped into the geosphere, except for water has its own sphere called the hydrosphere. Okay, so we'll cover the hydrosphere next lecture. So any form of water is not part of the geosphere, and biotic material is not part of the geosphere. So any living material or material that's recently deceased is not part of the geosphere. Now, eventually, when the material has been broken down into just what we call nutrients, right, then it becomes part of the geosphere, or can become part of the geosphere. Okay, and we'll look at this. So remember, I can't reiterate this enough. These spheres, whether we're talking about atmosphere, geosphere, hydrosphere, or biosphere, they interact with each other. They're intertwined with each other. So there's a connection between them. Organisms die, they decay, that's biosphere, but that material goes into the geosphere. Water rains down, okay, hits the surface, that's a hydrosphere, but that water can erode the geosphere. Okay? That water was coming from interactions with the atmosphere. Okay, so there's this connection between all the spheres, and that's why one tweak, one sphere is damaged, it can damage all the spheres. All right, so the geosphere, what is it comprised of, or what's its composition? So the geosphere has 3 composition layers, so 3 layers of different material. Okay, and then we're going to talk about its mechanical layers in a little bit. So 3 composition layers. The first layer is the crust. And we already looked at this a little bit on the first diagram. The crust is the outermost layer. That's the layer that when you're walking on the planet, that's the layer you're walking on, is the crust. Now, it's the outermost layer. It's not super thick, even though you might say, well, 100 kilometers is pretty thick. Not relative to the depth of the other layers. Okay? And if you took all of the crust and you kind of weighed it out or looked at its mass, it's less than 1% of the Earth's mass. So it's not a huge area, but it's hugely important area because of that ability for it to interact with the biosphere or life, right, and the hydrosphere. Right. So there are two layers to the crust. You have what we call the continental crust. Okay, so this would be like what most people would call terrestrial landscape. Okay, so the continents. And then you have oceanic crust, and this is the crust, the part of the crust that's under the water. Okay. So the continental crust is primarily granite. That would be this rock here. Okay, so that's primarily what it's made out of. That doesn't mean there's not other things, okay, other types of minerals and other types of rock that, make up the continental crust, but the primary rock is granite. Okay? And the oceanic crust, the primary rock is basalt. Okay? Basalt is lava rock, so magma rock. And you can see the pores there, you can see the openings where there's air bubbles, etc. We'll probably have a small lecture on some geology and geological differences between rocks, and so we'll bring these guys back up. I don't want to get into the details of how to tell these different rocks and how they form and things like that. Just realize that the continental crust is granite primarily, and the oceanic crust is basalt. Okay, so now we're going to look at the layer just below the crust. Okay, so moving from the crust and we're dropping into the layer that's below it, which we call the mantle. So again, the mantle is beneath the crust. Okay. If you take all the mantle, the Morovich portion of the mantle, the upper mantle and the lower mantle, and you combine them all together, it's about 67% of the Earth's mass. So it's a large portion of the Earth that's coming in the form of this mantle. Okay, the top layer of the mantle is called the Morovich discontinuity. Okay, and the Morovich, that's who discovered it. Okay, Andrei Morovich discovered this layer. Okay, he discovered it by looking at earthquake waves, earthquake patterns through the material of the planet. Okay, and you have a uniform kind of wave pattern moving through the crust. But when an earthquake sends out waves and you look or you observe these waves that are a little bit deeper, you can see that the wave pattern is not uniform. The wave pattern tends to dip and bounce and move around. And so in 1909, he discovered that indeed the material between the crust and the mantle, there's this small layer of material that was made of solid rock, or it consisted of solid rock. We call it the MOHO or the MOHO, just because most people don't want to say his last name all that often. But it is made out of solid rock and has these different causes waves, earthquake waves, to react to that material differently than they would react, say, inside the mantle or even inside the crust. So there's this unique region between the two. Okay, and it's important because the upper and lower mantle, this portion of our planet, is viscous and is lava. And so viscous meaning that it actually is semi-liquid, semi-solid. So it has the ability to kind of move as a liquid, but it's not quite a liquid. Okay, so viscosity is a measurement of how sticky or how material moves through a apparatus or through the environment. And so things that have high viscosity will typically move differently than something that has a low viscosity. Okay, so viscous material means that it's not solid. So the majority of the mantle is not solid. In fact, it's temperatures around 870 degrees Celsius to 2,200 degrees Celsius. And it consists mostly of iron and magnesium. This is where, magma, lava, whatever you would like to call it, this is where that material is often coming from. I shouldn't even say often. It is where the material is coming from. Okay, but that moho layer is solid rock, so it helps kind of form a barrier between the crust and the mantle. Okay. Majority of the information we know about the moho, the upper mantle, and even the lower mantle really comes from active volcanoes. Examining volcanoes that are active, examining temperatures that are coming off of these, material that's coming off of these, this kind of stuff allows for us to kind of come up with the science or scientific evidence for, well, what's the temperatures in this region? What's it made out of? What's the viscosity numbers of this material? Okay. All right, so let's talk about the core, or the third piece, the third composition of our planet. Okay. The core is two main layers, the outer core and the inner core. The outer core is liquid. Okay, so again, like the mantle, it's viscous. Okay, so it's fluid, it moves around, or fluid-like, it moves around. Okay, but the inner core is solid, but here's the interesting piece about the inner core. The inner core is hotter than the outer core. The inner core is hotter than the sun, but due to the pressure that all the other layers, the crust, the mantle, the outer core, puts on the inner core, it solidifies. So it's really neat, kind of a neat physics that's going on in our planet. And I wish I could tell you more about, well, what does the inner core consist of, but we don't know. We really don't know. We have lots of guesses, but we don't know, and I'll get to that here in a second. Okay, but going with the core and combining inner core and outer core, okay, it's about 33% of the Earth's mass. So you can tell that the inner core, outer core, and mantle makes up the vast majority of the mass of our planet. There's very little bit that we consider crust, where life interacts with that material on a regular basis. Okay, so temperatures in this region, extreme. All right, 22,000 degrees Celsius, 5 to 5,000 degrees Celsius, depending on where you're at. Okay. The interesting piece about the core is what gives our planet our magnetic fields. We'll dive back into some things about the magnetic field as we progress with animal navigation and things like that that are based on the magnetic field and other things that are based on it. Right. But this whole piece of the core that is interesting for a lot of scientists is it's hard to decipher what it is made out of. We know that iron makes up probably the majority of the core just because of the components of the inner and outer core and the mantle and things like that. We know that iron makes up the majority of it, but the other material that's in the core, we don't really know, well, what's that mixture? What's the other mixture? Okay, is it nickel? That was what was thought for a very long time. And now there's some evidence that it could be sulfur, that it could be silicon. Okay, so we don't know, and we'll never be able to measure it. That's just not possible. Well, I shouldn't say we will never be able to measure it. It's highly unlikely that we'll ever be able to measure it. Well, because of the depths, but also because of the layers above it. So the mantle, the depth of the mantle, the chemical composition of the mantle would make it very difficult for us ever to measure what is the core of our planet is made out of. Okay, so now we're going to talk about mechanical layers of the geosphere. Okay, so we talked about the compositional layers. We talked about the continental crust. We talked about the oceanic crust. We talked about the moho layer, the upper layer of the mantle, the lower layer of the mantle, and the inner and outer core, okay, of our planet. Now we're going to talk about mechanical layers, and we're going to go through each one of them and with a little bit of detail, not so far in depth that you are becoming a geologist, but a little bit of detail. So we have the lithosphere, the acetinosphere, the mesosphere, and then the outer and inner core. So let's go through these and discuss what role do they play in the mechanical portions of the geosphere. All right, so the lithosphere has two parts. It consists of the crust, both oceanic and continental crust, and the moho region of the mantle. Okay, so remember that moho region is the solid rock, okay, that's dividing the mantle from the crust. Okay, it's that top layer of the mantle. Okay, so together the crust and the moho region form tectonic plates. Okay, so you can think of the planet as a bunch of jigsaw puzzles. Okay, at least the continents on the planet as a bunch of jigsaw puzzles that you can see. Now there's more going on under the water. There's more plates under the water and more breaking up under the water, but the ones that we're going to kind of concentrate on are the ones that you can see, that you can visualize that they're above water. Okay. Now, those plates, they have the ability to move. The reason why they have the ability to move is the asthenosphere is that molten upper layer of the mantle. Okay, so right underneath the moho layer, that upper layer of the mantle is molten. It is viscous. It's fluid-like. And so because it's fluid-like, the moho can sit on it and move on it. Okay, along with the crust, it can move and migrate away from certain areas. Okay, it can move and collide into things. It can be consumed by things. We'll talk about plate tectonics here in a little bit. Okay, but the lithospheric plates, or the combination of the crust and the moho, they do move. Okay? And they've moved for billions of years. And this is the role that earthquakes play. We'll talk about earthquakes. Okay, this is a role that volcanoes play. We'll talk about volcanoes. But it all has to do with this interaction between the lithosphere and the asthenosphere and the movement of these plates. Okay, the mesosphere is that lower layer of the mantle. Okay. It's strong. It's different composition than that upper layer, okay? And that lower layer is part of that lower layer of the mantle, and that's what we call the mesosphere. And then we have the outer core and the inner core, okay? And mechanical, what's the role? Of course, we believe that it has a lot to do with the magnetic fields on the planet. Okay? But since we don't even know what the inner core's composition is, excuse me, it's difficult to tell what's the mechanical purpose of that layer. Okay, so we have, again, hot outer core, okay, and super hot inner core, hotter than the sun, in fact. All right, so let's look at plate tectonics real quick, just covering a little bit of the history. Okay, it was first described, or continental drift was first described by Alfred Wegener. He said that based on maps and looking at the continents and everything like that, he said that he thought that the continents fit together like a jigsaw puzzle and that continents were moving. Okay? He didn't actually have a very good hypothesis on how they moved, but he did come up with the idea of continental drift, the movement of continents over time. It was later, discovered how they move, etc., and a lot of his ideas had to be rejected. A lot of his hypotheses had to be rejected on how they move. But nonetheless, he kind of started the thought process of, are these continents actually moving, and do they move over time, etc. In the 1960s, we started figuring it out because we put seismometers out, and we put them out worldwide after World War II because we wanted to see if other countries were dropping nukes, nuclear bombs. And because a nuclear bomb will register on an earthquake meter or a seismometer, it will register on it as a wave pattern. It will cause a wave to go through, a shock wave to go through the crust of the planet, and it will be picked up. Okay? And so we were using it for that purpose, but then scientists started looking at earthquake activity, started looking at volcano activity, and they started figuring out that there are regions, there are belts of volcanoes, and there's belts of earthquakes, and there's other belts of volcanoes. And that this activity, when you would start to see volcano activity, it was happening along a line. When you started to see earthquake activity, it was happening along a line. And so that's where the ideas came from to look at plate tectonics and start really studying plate tectonics. Now, we have 9 major plates in the world that we talk about. Now, there are a ton of minor plates. But remember when I said plate tectonics, we're really concentrating on the terrestrial plates. So that's where, these come in. So North American, Pacific, Eurasian, African. Okay, it's really majority of we're actually talking about the continent, right? That's kind of on that plate, and that's where it's getting the name. That doesn't mean that the plates, end abruptly right after the land ends. That's not true. Okay, the plate extends out, depending on what plate you're talking about, out into the oceanic region. Okay, but these are the 9 major plates, and I don't know how many minor plates there are. There are new minor plates that get discovered or redescribed fairly often, so there's quite a few minor plates out there. But when we're talking, and we'll come back and we'll talk about volcanoes, and we'll talk about earthquakes, and we'll talk about natural disasters and their role that it plays in the biosphere, geosphere, atmosphere, and that connection between those. We'll come back and we'll talk about it. But real quick, I just want to talk about how a lot of these things form, or the generalists around some of these things. Okay? So you'll have hot spots or oceanic ridges where the lower mantle is sending up material, magma, okay? And you'll get volcanoes forming. Okay? So like the Hawaiian Islands is a great example of this oceanic spread and these magma pockets or magma sources that are coming up. Okay? But it's those regions where the plates are starting to move away from each other. They're starting to divide because new material, new magma is coming up, and it's pushing the plates away from that ridge. So it's called the spreading ridge, or the oceanic spreading ridge, and it's pushing it away. Well, those plates are moving. They're moving very, very slow, but they are moving. Okay? And they're moving in the direction of other plates. And when they come into contact with another plate, you'll get some actual physical contact, or what sometimes is called slippage, where this plate is starting to subduct. It's starting to go underneath another plate, and it happens all over, all around, lots of different plates. Now, there are lots of hot spots where you have lots of earthquake activity, but that earthquake activity changes as the planet changes. So it's not always been heavy activity on, say, California coast hasn't always been heavy activity for earthquakes, because there hasn't always been a heavy amount of subduction in that region. It's occurred in lots of other regions, but what's going on is that one plate is moving underneath another plate, and in doing so, they collide and they put pressure on each other, and then eventually that pressure releases, and it releases in the form of an earthquake. Okay? And then we get to feel the vibrations of that pressure release. That plate is going to subdue, it's going to go under. Eventually, it will encounter the lower mantle, and it will start liquefying that plate. It will start to take away the moho, and it will take away the crust, and it will magnify that material. It will turn it back into magma. Now, you also have regions on the continent. Okay, so you have oceanic spreading ridges, but you also have continental regions where you have new magma sources coming. Okay, now these continental regions are not spreading. Okay, these continental regions are often adding more material to the continent through the source of magma, and a lot of times these continental magma sources, they can be well, I don't want to say more violent, but sometimes they're quite a bit more violent. They happen less often because the magma is coming from lower down, and it takes a lot longer for the magma to form. But you can see examples of this on the western coast of the United States with the Cascade Mountains, are some of these magma sources. Those are all active. I shouldn't say all active volcanoes, but there's a lot of active volcanoes in that region. Mount Rainier, Mount Adams, Mount St. Helens blew up, okay, somewhat recently in 1980. Okay, but that is a range of volcanoes that still have magma source underneath them. Okay, and so we'll come back again. I don't want you guys to concentrate heavily on the geology behind this, because we'll come back and we'll talk about volcanoes specifically, and we'll talk about earthquakes specifically. But I just wanted to hit on a little bit of plate tectonics as we progress. Next time we're going to talk about the hydrosphere, or the role water plays on our planet.